isotopic character of a chromite is sitting in that laurite. And this is very strange because virtually all the chromites in the Bushveld complex are very radiogenic, but the EGM-rich ones are surprisingly less radiogenic.
Those things are bottled up, and they can't see the radiogenic ingrowth.
Yeah, but
that's the basis for the work that people like Paul Griffin and Silver have done. They look at these things.
Yeah.
You can get really
Okay, next up, we've got Zoja Vukmanovic talking about use of EBSD in the study of chromites and implications for
I was cheating. There is no really implication for reaching. That's just to make my title better fitting. Let me just see if I can. Yeah. So I want to thank first to Marian, who's my PI during my postdoc days, and especially actually Penny Wieser. Penny and I had a similar problem of how to differentiate between differently formed aggregates. She was interested in olivines, I was interested in chromites. So in 2019 or something like that, we published a paper on kind of a team study of chromites and olivines and how they form aggregates. Yeah, basically. Killian helped us a lot. Rudiger Killian helped us a lot in writing codes that I later on reused for further investigation of Bushveld chromitites. So I'm also here to tell you that you should all use EBSD because it's one of the best and easiest technique ever. So I'm going to give you a little bit on a quick intro into EBSD technique. And I'm going to cheat again because Sarah said we should kind of show already published data and well-established. I'm going to show you new data. It's not published, but it's going to help you also later on if you listen to Marian Holness' talk tomorrow. Some of the EBSD, maybe the EBSD part will be more clear. And the example here will be Marensky Reef. So EBSD technique is kind of complementary to the SEM. So it's an additional detector that will, that if your sample is here, your sample needs to be tilted 70 degrees and it records these Kikuchi patterns. And with these Kikuchi patterns, you can identify different phases in your rock. And also you can look at the crystallographic characteristics of these minerals. And here is the sample that I'm later going to talk about, which is a phase map of yellow chromites, blue is plage, and I think this is a pyroxene, not sure which one. So I'm going to talk today about crystal orientations, misorientations between the grains, and grain sizes and shapes. Well, I'm going to just mention grain sizes and shapes. I'm not going to talk about deformation within single grains, though actually in Marensky Reef, there's some really interesting story how and what is deformed, but I'm going to leave for the next symposium or for next year's Marensky Reef 100 years anniversary. So can I find this? Never mind. So this is how orientation map looks like. You see all these the grains that are colored and in fact chromites, and each grain is orientated close to one of the low symmetry axes. So low symmetry axes are 111, 110, or 100. So these are the simple crystallographic axes that we know. There are many more axes that are in between those kind of basic ones. So, and you can see already that here you have a bunch of different colors. This map is produced so that we are looking at the orientation along x direction. So you can change that in your codes and in your softwares. What is really nice as well about EBSD, you can overimpose the shape of the crystals. EBSD won't give you exact shape of your crystal because we don't know that, but you can assume. So for chromites is easy. We can put an octahedral on top of it and it will fit its orientation data that you have from the map. You will see later on, I tried to do the same with plagioclase, but plagioclase is much more difficult, especially when it's interstitial. You cannot give a good estimate of orientation. Of the grain shape, sorry. But if you would have a strong plagioclase fabric, you could come to the conclusions sometimes what shape your plagioclase is. Because unlike Steve, most of us only look at the rocks in 2D and not 3D. This is another map actually from UG2. You see a lot of grains. And they all seem random colors. And if you plot them on a pole figure, did I miss my pole figure data? Sorry. Oh, yes, I missed the pole figure slide. So this is what are the pole figures? So they are crystallographic representation from your crystals. And often, you know, when you look at the pole figures, there is not one point. There are 3 points for 1, 1, 0, 0, 1 to 5 for 1, 1, 0. Is it 5? Yeah, 6. And 4 for 1, 1, 0. 1, 1, 1 axis. So these are all stereographic projections from the axis or planes in a 2D projections. So you get something like this. So it looks like a lot of data, but it's a little bit less. It's still a lot, but it's a little bit less. When you look at these kind of pole figures, it doesn't tell you anything. It tells you, oh, it's a big mess, a big cloud of data. So you can counter them. With chromites, it's very rare that if you look at a bulk texture, it's very rare to have a texture. They're cubic crystals. They don't have shape preferred orientation, for example, like plage can. So this is the texture you get, 0 texture. The chains. I love Steve. He's my supervisor from my PhD supervisor, but I get like goosebumps when I hear chains. You can see chains. If you look closely here, you can see grains that are in similar shapes. But as he showed you, they are not really chains. They're just part of the network of the grains. So in this particular grain, the harder you look, the more chances there are that you will see grains that are in a similar orientation. But again, you will need to quantify that. So the way to assess crystallographic orientation, apart from just looking at the texture, is looking at the relationship between the neighboring grains. And John Wheeler published an amazing paper. I have a list of references in the end. It's a bit hard on crystallography, but you can define the relationship between 2 grains by looking at the axis between these 2 grains and angle between these 2 grains. So for example, if you translate this to the same orientation from here to here, you need to rotate it 1 grain for a certain angle along the certain axis. Does that make sense? So, and these are very important parameters to define the relationship between neighboring grains. So we are talking about misorientation angles and misorientation axes. Each crystallographic group has theoretical distribution of these angles. If you would have a random distribution of chromite grains, they would fit to this red curve. And that's the same with the axis. The blue is the real data, and the red is theoretical distribution of these angles. So I'm not going actually to go into this because this is just an example. This random distribution of axes now can be normalized. Well, it can be actually also compared to the measured distribution. So later on, I'll show you what happened when you take the theoretical out of this measured distribution. So you can get away, you can examine the peaks that you think you see. I realized that actually I'm not talking in this particular talk about grain shapes, but it's really important, especially if we want to understand the magma dynamics. So are we seeing sorting of the crystals? So for example, if we have a slurry, we would hope to see some grain sorting, which we, with chromites, again, unfortunately, or fortunately, never see. So we would then look at the grain shape along a certain section of the chromitite layer. Or if you're looking at the silicates, you can look at the aspect ratio and compare that to your textured or absence of texture that you can see. So these are very important, very useful microstructural characteristics that you can get from EBZ data. Chromites community has so many methods, models, how they form. So I just put 4 here, and I'm sorry if I missed something. I'm a kind of like an intruder into chromite community because I focus so much on microstructure in my research that I'm not very good on chromite solubility or trace elements in chromite. So today was very useful for me, for example, this morning to listen about this, about the solubility of chromites in magmas. So what I try to do with success or less success is just to see what microstructure is telling us. Can we actually identify anything from these list of models? Can we see more processes than one in some of the model, in some of the samples that we look at? So I think actually Rice sparked the interest of how chromites nucleate with me, and he sent me some samples very kindly. So, and there was this big thing about chains again, like how the chains forming, are they chains or not? And I'm not going to talk a lot about what is homogeneous nucleation or what is heterogeneous nucleation. And I said you might hear more on from Marian on Monday, but on Tuesday, but maybe she said maybe not or something, I don't know. But like I'm going to show you one experiment. When my first year at Cambridge, I worked with Marian and Jerome Neufeld of pouring in very saturated ammonium chloride liquid into a cold chamber. That was actually a mistake that I put it in a cold chamber, but it was kind of like a learning process for me. And what I saw is that there was, of course, heterogeneous nucleation on the bottom and on the top, because it was not covered, so it was in a contact with the air. But I had this burst of nucleation within the liquid. So with the heterogeneous nucleation within the bulk liquid, it was very, very hard to get. So I had to be careful about the conditions. I had to be very careful about concentrations. But I managed, I think actually I managed better in this example. I just couldn't find my old movies to get actually this burst nucleation. The key was that it had to be saturated liquid. So I'll come back to this. I call it snowfall. In literature, you can actually find it as aqueous crystallization of so, and there is a paper here, and that paper cites a lot of other papers that talk about aqueous crystallization. So my bane is that I always work on a couple of samples, and I always think it's not enough. Like you get samples that you inherit from somebody, or somebody sends you samples. Can you look at the EBSD in this? And I always feel inadequate because, as you saw from today, 3 talks on variability of chromites in the field, it just seems a bit like a Don Quixote-esque searching for a holy grail, in like looking at 2 samples when something is 2,000 kilometers wide. It's a bit weird. So I thought about when I started preparing this talk, I thought about tale of 2 chromitites, a Marensky reef versus large thick chromitites. But then Marian will talk about UG2 more, and I will just show some nice examples of Marensky reef, and then we can discuss later in the week about the differences. I think actually the work Marian and I did, and Brian on the UG2 was much easier because we actually had much more silicates to look at as well. Whereas Marensky reef, I find it actually quite tricky. But again, this picture from Rice from 2017. I just changed the color. This fits more to my color scheme. I was really lucky that he sent me generously these two samples because I thought this is really nice samples to analyze. So these are his undercutting Marinsky reef samples, right? And I wanted to see how they're different from UG2. We looked at UG2, yes. And they're surprisingly not that different in one way. In a different way they are. But so as you can see, I analyzed this sample here and this sample here. So this is really nice sample. And you can see here, this is a phase map of the two samples. I probably won't talk too much of this because it's quite small sample, so it doesn't tell me a lot, but it's much better indexed. What I mean, like you see how here, there are these blank spaces because I didn't get the data from there. But so this is just kind of like a petrography image looking at the phases that are present here. Again, so these are the orientation maps, again, along x-axis, and there are different colors around, you know, there are some, you can see chain here if you want, like there is a purple, red, or, you know, there are some crystals that are similarly oriented. You can see actually here a very large, like long, so it's not large, but like it looks like a caterpillar with a very low, like almost low angle boundaries. Because if I would have plotted grain boundaries here, you would see them, but they're below 10 degrees. So there was some sintering going on, like, because you can see the shapes are like chromite-like, but it's not plotting my grain boundaries. So they're super low. So are they recrystallizing, and what's happening there? I don't think it's a growth feature. I think it's a post-solidification, subsolidus modification of chromites. But if we think about settling, you cannot talk settling on this sidewall, like, and not because I'm not even thinking about, you know, if it's realistic or not, but you can see the grain size distribution and it's all over the place. So it's not, you don't have any kind of a distribution of larger grains versus smaller grains. They're quite heterogeneously distributed. Paul figures don't tell us anything. We see that they're all random. We see a little peak here, and this is normalized. So I took out the theoretical distribution, so kind of the expected distribution of the chromites, and I got the peak in 111. And these are actually twins. And if you think about epitaxial growth or self-nucleation, however it is called, the only way that it's energetically favorable is actually forming twins, which can also be formed differently. But in any case, this is not a lot of twins. And if I measure how many twin boundaries we have less than 10%. I think these are maybe too small numbers, but I think they are in terms of between 6 and 10% of twins present in those rocks. This is a plage map that I'm going to, I think, when did I mix again? Something, no? Okay, sorry. So I also wanted to look at the plagioclase relationship with the chromites. I'm going to talk more about plagioclase itself, but if we have an in situ growth, we also want to test what is the relationship between chromite and the underlying or like the wall, the anorthositic wall that they are growing on top of it. And we can test the epitaxial relationship between different phases. And Hammer et al. In 2010 look at the clinopyroxene with magnetite relationship. And so this is a clinopyroxene map. This is oxide, Paul figure, not map. And if we overlap the two, you can see how these axes overlap. So they're parallel to each other. And that's their crystallographic relationship between the two, if that makes sense. They're sharing the low symmetry axis between each other. So they have a specific crystallographic relationship. They're not randomly growing on top of each other. I here just put in what I am expecting. So what I was looking for was such a relationship between chromite and plagioclase. It's a very difficult thing to compare axes in a quantitative way of different phases. And I'm not going to explain the crystallography behind it. You can look at the Krakow et al. 2017. This is a random data of chromite plagioclase axes and angles from this sample. There is zero clustering in a random subset from the sample. But in a more easier way to look at that is in a 2D cross-section of that weird fundamental region. And the only thing that we can see, so these are the theoretical position of the axis. They are here, labeled here. The only peak that I have is between chromite 100 and plagioclase 100. But it's a very small peak. It's a peak, there is some, but it's not very prominent. However, my next task that I didn't do for this workshop and I wanted was actually to pick up those crystal pairs that have this relationship so I can see where they're coming from. So what is my model? I don't have a model. I don't want to have a model. But for me, instead of having complex models, I'm thinking about my experiment from my first year at Cambridge, where I had a burst of crystallization, burst of nucleation of the chromite crystals who are forming accidentally these networks. So they're not, okay, I'm going to form a chains or I'm going to form crystallographically controlled structures. I think it's just, as Marian told me today, a boundary layer formation. So you can argue, because I'm not good at this, if this is a reaction between two liquids, if this is coming of the input of the hot magma saturated in chromites, forming these in situ chromites. I do believe they're in situ. I just think they're randomly bursting like a snowfall, forming along the boundaries. Why? I'll leave that to you. But this is my interpretation. So what next? I'm still very amused with these plagioclase crystals. I think they're really cool. Sorry for jargon and not scientific language, but look how they grow. They grow literally from, so we have this random, like almost randomly oriented, this remelted anorthosite. And then from the contact, we have these spades going towards inside the reef. And so this is our plagioclase. This is 010 axis is blue, 001 axis is black. And I was hoping to get better, kind of more spectacular image. They are growing randomly. I looked at also along the distribution of these plagioclase that are going through towards the reef. They are random, but they are growing fast, and they're unlike chromites that has a lot of nucleus there. These plagioclase, I guess, would have a small nucleation rate, but fast growth. And there is no particular, so I split this image into three so you can see it better. There is no particular preferable orientation of these grains. I looked at just at the plagioclase along the contacts. The problem with Paul figures, if you have a low amount of data, you will have peaks that don't mean anything. So you need a better sampling. So ideally, I wouldn't want more of these type of samples. And I also would really like to look far from this remelted zone and look at those anorthosites that are further away from the reef, so we can compare actually the texture along the contact and within the anorthosites. What I would also like to do, so please send me samples, is actually look at the chemistry between the footwall and these plagioclase that grow along the within the reef. So Steve mentioned, Steve Barnes, that they have different strontium content, which I don't know much about chemistry, but I thought that was cool. And that it can maybe tell me something about remelting of this football or like what is going on. And so I also think that the plagioclase is growing after the chromite is already there. So and I also, yeah, so I said everything. So I think that's it. So I think that we can postulate about exact mechanism, how they form, but I wanted here just to tell you what you can get out of microstructure. Ideally, you would want to look more into silicates. You would want to look at more samples than 2, but don't forget microstructure. Am I too fast? Probably. Okay.
Any questions?
Thanks. I certainly like this story much better than the one with the settling clusters of chromitites. But can you show, please, still let me touch you a little bit with this model.
With my model.
Yeah, with this one, yeah. You know, the problem here,
No?
as I see it, just for future thing, you know, we are sitting in the middle of the bushveld complex. Rocks are hot like a hell. And to the way I understand you would like it kind of boundary crystallization, it means that you are cooling it. And that's problem. You cannot really cool the magma along the margins. It's difficult.
Why not?
Because they're hot.
But that's why it's happening only on the contact.
Yeah, the contact, if the contact with intrusion, that's fine, but that is in the middle of the hot intrusion.
But you're bringing on your new magma on something that's already cooler.
Not necessarily cool. It's hot.
And I can feel Marian like already. It's also a compositional boundary.
And then another thing, you know, as soon as you form it like that, you're showing in above. If you go below, they go. As soon as you form in the chamber, the melt, and they're hanging, they're going to settle simply and go to the bottom, not touch to the margins.
I think, like, I always thought, I might be wrong, because I'm not going to remind you what you told me once over Zoom when we discussed. But like,
yeah.
Wait, I also think that it's impossible to have 0 nuclei while you're coming in with a new magma. So I think that I think magma with 0 nuclei is.
No, that's fine, but the nuclei will be everywhere, not along the margin. That's a problem.
I think like when you're coming in with your new magma, I'm sure it already carries a little bit of nuclei that then just helps out the further growth of nuclei, like, you know, like along the contact. And also, you know, I don't really comprehend this like settling down the crystals along. So you're not putting magma into a water, you know. You're not having chromite submerged into water that they're just going to fall down. Like it's. I know that chromites are.
Let's stop. Right. Thank you.
Well, I have like 2 questions. So the first is quite easy. Can you use thin sections?
Sorry?
You can use thin sections with this.
Thin sections.
Yeah.
Yes, yeah, they're all thin sections.
Okay, yeah. And then the second, so do you have some sort of explanation? Because that was quite interesting, the thin section image that you have the thin layer of chromitite there, and then the like an oikocrystic but still euhedral grain enclosing the small. How do you interpret that? So please teach me.
You mean the plagioclase?
Yeah, the plagioclase.
Well, I just think
because you mentioned that
they're very large. So in UG2 hanging wall, they're huge single. So I don't know, I don't think Marian will show that, but if you look at our paper from 2023, the size of the oikocrysts, it's not euhedral, it's all interstitial, but it's the size of the full thin section. So the chromitite, not the chromite, the pyroxenes are like, seem like they're stuck in the huge single crystal plagioclase. why it took so long that it goes like, well, actually, I don't know how long it took, of course, but like, I don't have explanation why it's so large. I at one point, like when I was preparing for the paper and stuff, I thought it might, I know the water here is like a forbidden word, but maybe like that, like fluids had a, like some role in such a huge growth. Because in UG2, for example, within the chromitite layer, you have so much mica as well. So is the late plagioclase growth enhanced by this fluid? I don't know, but I'm not maybe right person to talk about that.
I just remember that you said that the chromite grains there, they were first there. Then I was just thinking that it can't be because they can't be like flying around. So I was just thinking that it might be some sort of a super saturation or something. Or
I think that Steve doesn't agree with me that they are first, right,
yeah.
Steve? You think that the interstitial phase grow at the same time as chromites?
At the same time.
Not here. Okay. Okay, sorry.
In the UG1 as well, as you can see it growing down from the top of the sea.
Yes, you can.
I think probably not very much, but definitely.
You can't have the chromite and the plagioclase on the liquidus at the same time. The chromite is far too rich in chrome. At least if you're using B1, the plagioclase has to come after the chromite. It has to be more fractionally.
Any other questions?
Which agrees with the text.
So can you tell us some characteristic, maybe microstructures to distinguish the chromite formed by sorting and setting or formed by the in situ crystallization? Is
So
there
ideally, like
Yeah.
what Rice was before saying, this self-nucleation. If you would have self-nucleation, it would have to be crystallographically controlled. So your distribution of certain axes here. So if you would have a huge peak in particular axis, particular angle, I would say that's an in situ growth.
Okay.
But that's only for chromite. So for other oxides will be different and more difficult. So for example, in magnetites, it's impossible to say anything about primary structure because they're completely recrystallized. They change the grain shape, they change the beauty in chromites when they're enclosed with the interstitial phases, it preserves the primary.
So you mean the chromite in UG2 is also recrystallized?
No, the one that I looked at was not
Yeah.
recrystallized, but there are some probably in UG2 as well, but you can see the change, the grain shape is completely changed. It's like more like kind of
Not euhedral, right?
yeah, like euhedral, and there is no interstitial phases in between, so the grain, initial grain shape is changed.
Okay.
I think we'll, all right, I think we'll break for tea and coffee now. Would you back? Slow by now. Leave that slide up. Thanks for leave that slide up.
It's not very like it's just like easily run that, but it's fancy.
Good answer to it.
Underground is actually very, it's for condition, very few people actually, actually. Well, if there's no underground, that's. And the classic is that is. The pressure. The actually was a good. No, I mean, so what happens is this is. Oh, it's a big, why females, especially this one, twice. When you've got this, you've got really strong, small balls. So you look at sayings, you've got loads of condition might be expected to just have. But again, market this is
It's being built on by far smaller scale increments than
previously on that, yeah. But they don't have that same effect, so yes,
really well that the industry should flash.
Yeah, that's very cool. That's going to help. Now, Jerry, when we look at the calcium antiphase in chromite, it's exactly the same. Very much is. And Jerry, actually, nice is right. Generally speaking, yes, and they usually see a little bit more, a little bit of old compared to
We find that it's associated with this.
But I mean, that's part of the argument. Even those fences. That's yeah, well, okay, we can go. 应该是石膏嘛，是造出的。
这个楼这一层有吗？还是你觉得那个楼？
其实这个楼，但是你转半天不是去那个楼的，
行，可以。
那个转半天我会说几个呢？
给够凑合的，因为我发也是。这怎么样？就是，你看这是啥子？还是蛮好讲。怎么意思？还在做吗？那小蝴蝶呢？那小蝴蝶呢？天理啊！
Oh, right. Yeah. Well, I mean, it's the more you look at these things, the more it's like, was it? I think it was you that said it. A lot of people don't understand. Oh yeah. Fortunately, I'm going to be very sympathetic to you guys. Yeah. You know, because it is some of the best stuff. It's just tough to take it. Yeah. Is it representative? Is it representative? Yeah. I didn't close out the door, so we're still on share, so. Okay. Straightforward.